Okay, so where we ended last time, we ended with a particular um, form for uh, the magnitude response. So we'll see as we start working with the Bodie method that term appears over and over again. So we want to look at a term of the form um, 20 log of 1 plus j omega over omega c. Where I ended last time, I had a term like this in the denominator, and I had 1 plus j omega over omega p. But in general, we'll see that this term might actually appear in the numerator. I might have multiple terms like this appearing in the denominator. And so instead of using omega p, that particular r over L value, I'm going to just generalize that and call that omega c. Of course, the magnitude of, again, this has a real part of 1, an imaginary part of omega over omega c. So the magnitude of this complex function of frequency would be 1 squared, which is 1, plus omega over omega c squared. Okay. Now, here's where the Bodie method comes in. I'm going to actually approximate this function so that I can graph it on special paper. But I'm going to consider two extreme values for omega. Actually, the first case I'm going to consider is when omega over omega c is much, much less than 1. Then if I look at this term, the sum of this term is small compared to 1, so I can approximate it just as 1. I've got the square root of 1, and 20 log of 1 is 0. So for frequencies below this, whatever this omega c value is that might appear here, I'm going to approximate this term as 0 dB. Now, at the other extreme, when omega over omega c is much greater than 1, I'm going to neglect the 1 term. Then I'll have the square root of omega over omega c squared. So that will just reduce to 20 log of omega over omega c. Okay. Under this condition. So let's actually look at this term, this 20 log of omega over omega c, for a couple different ratios. 20 log of omega over omega c. Okay. Now, first we'll take the case when this is equal to 1. Yeah, I know that the approximation is only valid when omega is much greater than omega c, but I'll take this kind of as an extreme case. When this is 1, I have 20 log of 1, which I know is 0 dB. And when it's 10, I'll get 20 log of 10, or 20 dB. When it's 100, I'll get 40 dB. And when it's 1,000, I'll get 60 dB. What I note here is as the frequency increases by a factor of 10, as omega, when omega is equal to omega c, then it's 10 times larger than omega c and 100 times larger than omega c. What I see in this dB term is what's called a 20 dB per decade increase in this term. So again, we're going to look at graphing this term, and this is what I want to remember. As my frequency goes up by a factor of 10, which is called a decade, then the magnitude response increases by this 20 dB per decade rate. So what we'll be using is special paper, semilog paper, which is logarithmic on the x-axis. So sometimes it's called semilog x paper. But what we'll have here on the x-axis, which will be our frequency axis, omega in radians per second, it'll be laid out actually in and factors of equal factors will actually be factors of 10. So let's say that omega c may turn out to be somewhere between 100 and 1,000. So again, on the semilog paper, equal units here actually become factors of 10. And so if I could continue to the left, another equal unit would actually be a tenth, then 1/100th, then 1/1000. I'd never get to zero, a value of 0 omega on this semilog X paper. But my Bode approximation, where I'm trying to graph this 1 plus omega over omega c term, j omega over omega c term, is, let's say omega c is right here. Based on these approximations I have here, what I have for this graph is this term will be equal to 0 for all frequencies less than omega c. Okay. And then for values of above omega c, so this would be 10 omega c, this would be 200 omega, I'm sorry, 1,000 omega c. Okay, I'm going to increase at a 20 dB per decade rate. So this would be 20. Continuing this would be 40. Okay. And so this is my graphical approximation to this term, and it actually turns out to be pretty good. When omega is equal to omega c, this becomes 20 log of the square root of 2, which actually turns out to be 3 dB. So it's slightly off here, right here at the knee or the corner, but so the real plot of this thing would actually look something like this. But this two-line straight line approximation actually gives me a very good approximation to what the frequency response of this thing looks like. So we'll come back to this and we'll return to our RL example and graph the magnitude response of that using this Bode technique.